In your book, you have to check the example. I just don't have it handy. So here, the vector space V is again Rn, and A an n times n invertible matrix. And then we define for U and V in Rn, we define an inner product based on this matrix A. So it turns out U comma V is defined as A U dot, so this is the old dot product, A V. So this is matrix times vector, and then do the dot product. Keep in mind, the dot product is nothing else than multiplying the transposed vector times the vector. So it turns out this is the same as A U transposed times A V with the matrix product. And remember, transposing always flips the order. So this is nothing else than U transposed, A transposed, A V. So this is an inner product based on an invertible matrix. And so again, this product is nothing else than the old product, but instead of taking just the vector U and V, you actually take first multiply by A. And here it's important for the invertibility. Otherwise, we cannot argue the only way that a dot product can be zero is only the zero vector. Okay, and for this now we can actually show now the properties, and then later on, maybe tomorrow, I'm not sure how far I can go, I can also show this actually includes the dot product, the weighted inner product we just saw. So property number one is very fast. U comma V is the same as AU dot product AV. But dot product is symmetric, so I can actually flip here. So this is the same as AV dot product AU, because that's what we did in section 3.2. So it turns out this is the same as V comma U. So that's good. Part 2 is U plus V comma W. So I should say also here U, V, and W are in Rn, our vector space. And then later on alpha is in R. Then we have this is the same as A times U plus V dot AW. Matrix multiplication distributes, that's our section, I think it was 1.4. So this is AU plus AV dot product AW. And now dot product distributes, that was the start of today's section. That was one of the reasons why we asked for the same property for our inner product. So this is AU dot product AW plus AV dot product AW. And now we see this is just our new inner product U comma W plus V comma W. So this is equal to this and this. So the second property of a dot product is of an inner product is also satisfied because of the properties of the corresponding dot product. Next property is I do alpha U comma V, alpha a real number, U and V are vectors. According our definition, this is A alpha U dot product alpha V. Now we use property of matrix multiplication, matrix number matrix, also this matrix is a vector. That's something we did in chapter 1.4, section 1.4. So the alpha can go here in front. So this is actually alpha AU dot product alpha V. So now we have vector, dot product with a number. For the dot product, we know we can put the number in front or to the second, whatever we like. So it turns out this is alpha AU dot AV. And again, this is our new inner product. Okay, and so again, that was very easy. And we have not used at all until now that the matrix is actually invertible. So that must come somewhere, and it comes now. So the first step is, if you calculate u comma u, is this always larger or equal to 0? Turns out this is again pretty easy because it's a times u dot product a times u. And for the dot product, we learned if you take twice the same vector, it's always larger or equal to 0 because it's just the sum of the squares of the components. So that's fine. So again, the invertibility must come in at the last step again, very similar to the examples which we had now about functions. And so now we do u comma u equal to 0 if and only if, according to this, a dot u, this is matrix multiplication, this is dot product, equal to 0. But now, because of the property of the dot product, we know a dot product of a vector with itself is 0 only if the vector is 0. So if and only if a times u is equal to the 0 vector. And now this is actually where invertibility comes in. If a is invertible, then au equal to 0 means u equal to 0. And that's the last property we need. No? So here comes in that A has an inverse. So if you have an invertible matrix A, then A times X equal to 0, that was in section 1.64, has only, the homogeneous system has only the trivial solution. That was 1.64. Now, instead of calling the unknowns X, the unknowns are called U, but that is still the same property. For an invertible matrix A, the homogeneous linear equation system has only the trivial solution, and that's exactly what we need here. Okay, so now as an example, which now connects this example to the previous weighted product, we take V equal to R2, and the matrix A I take as 1/3, 0, 0, 1/2. So then I take this product. So if you take u equal to u1, u2, v equal to v1, v2. So what is now u comma v with this matrix A? Yeah, it is actually, it's the dot product between this matrix and this vector, dot product. This is, it's kind of too many dots here. No? This is matrix vector, this is dot product. And then we do here again, 1/3, 0, 0, 1/2 times v1, v2. So now I calculate this vector in this parenthesis, and means the 1/3 goes just to the u1, and the 1/2 goes to the u2. This is the first parenthesis, then this is our dot product. Now we make the second parenthesis. 1/3 goes to v1, and 1/2 goes to v2. And now finally, what is dot product? You multiply this times this, and this times this, and you add it up. 1/3 times 1/3 is 1/9. u1 v1 plus 1/2 times 1/2 is a quarter u2 v2. So it turns out if you use this matrix, the inner product for the matrix is actually our previous defined weighted inner product. Remember, I put this in the previous slide. Weighted inner product with first weight. Okay, sorry, that was now in the last week. We have these kind of thing. I try to share again. Do you see this again?
Yeah, we can see it.
Okay, sorry, I don't know what happened. My my doc cam just broke down. At least it said it was stopping working. Okay, so here we have the weighted inner product, and we see this matrix, which is an invertible matrix, will give us the same inner product. So it turns out that was a special case. So with the help of matrices, you can generate more general inner products. No? And so this is another example of an inner product of Rn. And when you just think about the example we had before, when I showed you the ellipse, what you really do by doing this is you change the geometry of, for example, R2. Also a circle is no longer a circle, it becomes an ellipse. Also the angle between vectors changes. And again, why do we do this? Because, for example, in physics, when you have measurements along one axis has maybe another error or mistake attached to it than a measurement along another axis. Yeah, so that is, for example, one reason why people would do this. Okay, so that was a little bit fast here at the end. I hope still there are some homework problems where you calculate inner products like this and I think they give you the matrix all the time, and just do the same thing what I did here, just with a different matrix. No? And so this finishes 6.1. So the only thing left is 6.2, which kind of closes the circle again, because it connects now the inner products again with linear equation systems. So at least I like to go over this tomorrow. So you see one more time we come back to linear equation systems. Okay, and I would like to do this tomorrow. So if there's no more question about this example or the inner product with the help of an invertible matrix, then I would stop sharing. Hopefully everything works now when I do this. And I post the videos later, and office hour again 3, otherwise tomorrow again for our last lecture.
Professor?
Yes?
So I saw on Kula courses that you listed all the chapters that are going to be on the exam.
Yes.
Is there any way that you can also include some of the exercise numbers so we can practice those? Or
but but when you look, just go the homeworks, no? You have the numbers of the homeworks, no?
Okay, so
yeah. Also, if you have enough time, step number 0 for preparing for the exam is really make sure you go over your notes, that you know how to do all the homework problems. That's for me step number 0, no? Before you do anything else. Yeah. And then I think I mentioned before somewhere in an office hour or so, if you have additional time, I'm not sure, then let's say for the written homework, I assigned problem number 18 and 19. Now you see, for example, oh, but 20 and 21 are similar. Then just do 21. So you have an additional where you have actually the solution at the end of your book, no?
Okay, thank you.
But I would always start, also before you do things like this, always start with making sure that you know how you did all your homework problems. I mean, homework, I mean written and online, no?
Okay, thank you.
Yeah, so having good notes there helps.
Thank you.
Mm-hmm. Any other question? Okay. Sorry, yeah.
I said no, thank you, Professor.
Okay, thank you. Then see you either later or tomorrow.